Today we are going to look at the ear, and the first structure we're going to start with is the outer ear or the earlobe. This is known as the pinna. And the pinna basically serves as a funnel, which is going to funnel sound down an internal tube, which is called the external acoustic meatus. The purpose of this tube is to funnel sound onto the tympanic membrane, which is what you would call the eardrum. As sound enters the ear, it will be funneled onto that tympanic membrane and cause it to vibrate. The vibration of this tympanic membrane causes the bones of the middle ear to vibrate. These bones function like levers, and what they do is they take the sound, which comes from air, and they make it stronger so that it actually moves fluid within the cochlea, which is the inner ear. The bones are the malleus, which is Latin for mallet, the incus, which is Latin for anvil, and the stapes, which is Latin for stirrup. Attached to these bones are ligaments, and these ligaments can tighten in the event that there's a very loud sound. And in tightening, what they do is they keep the vibration from occurring, and that keeps the sound, loud sound, from damaging your inner ear. So if you've ever noticed when you've heard a really loud sound, it seems almost like you can't hear anything for a little bit. That's why. Also within the middle ear, we have this structure. This is called the eustachian tube. The whole goal of the eustachian tube is to balance out the pressure between the inside and outside of the eardrum. You can imagine if the pressure inside the eardrum is too high, it's going to cause the eardrum to bulge out and it won't be able to vibrate quite as well. So what this tube does is it kind of creates that pressure release valve. You've probably noticed this if you've ever been on an airplane and you've had your ears pop. So what happens when the fluid in the cochlea is moving? What does this do and how does this lead to hearing? If you were to take a cross-section of the cochlea, this is what you would see. It's a hollow, bony structure, and it's got several chambers in it, and these chambers would be filled with fluid. This is the fluid that moves. And what happens when this fluid moves is that it causes movement in this basilar membrane. And the basilar membrane is going to cause these hair cells here to move back and forth against what's called a tectoral membrane. This back and forth movement is going to bend these hairs. And in bending these hairs, it's going to allow opening of ion channels. These cells within the ear are called hair cells. And they look like this. They actually have these cilia on the top of them. And what happens is when that fluid moves, it pulls on the hair cells and it causes them to lean. I always imagine the cells looking something like this. This is Michael Jackson doing his anti-gravity lean, and you'll notice that he's leaning almost to the ground. In the case of these cells, that lean is actually very important. What that lean does is it actually causes these hair cells to pull on each other because the hair cells have between them something called tip links. So when the tallest hair cell starts to lean, it pulls on all of the others. And this pulling stretches the cell membrane. And by stretching the cell membrane, it opens ion channels that are located on those hair cells, and that allows the ions to enter through those channels. Now, in this case, these ions are actually potassium because there is a lot more potassium outside of the ear than inside. But potassium is still a positive ion, so in terms of our action potentials, it turns out that we still get a positive increase in voltage, and that's the signal that gets relayed through the nervous system.